My name is Monkia Nawrot.
Hi, I'm Marcin. I'm part of Monica's team.
So we both work on cloud functions based in Warsaw at Google. And we are going to talk about serverless that we do at Google. And we are going to share with you some internals. So maybe after the talk, you will know more how serverless works at Google. This conference is about serverless, and serverless is really, really awesome, as we all know. The first and the most important thing, you don't have to manage the infrastructure. So no more servers, no more maintaining, configuring servers. Like everything happens magically. Security patches are applied. Everything works as intended. Also, you as a developer doesn't have to care about any load spikes. So when the traffic goes up, like the number of servers, instances, it's going up, and you don't have to worry about that. And also the good thing about the situations when the traffic changes is that you don't have to pay for any unused cycles. So if you didn't use serverless, you have to run the machines that would be unutilized if the traffic is low. So, and now with serverless, you can concentrate on coding. So, the best and the most fun thing, because what else is to do? But the thing is that it's not exactly the case. So, serverless is kind of a black box. So you deploy your functions, they work, but sometimes you see that some invocations has increased latency, or maybe sometimes you see some error rates, or maybe you hit some quota limits that might be very not obvious. In example, you use a library that on each invocation resolve a DNS, and you hit the DNS quota, which is kind of weird and maybe not that obvious if you're running that on your own infrastructure. Also, you observe a bit different behavior on your machine than in cloud. And finally, also the managing of functions may differ. So you are deploying a new version of your function, and it suddenly gets slower. So this is the agenda of our talk. So first, I would like to talk about serverless and how we build that on GCP, so Google Cloud Platform. Then I would like to explain what happens when you deploy a function and what's happened when a request is received by your function. And finally, we are going to talk about some best practices and show you a real-life example, so we can observe how the behavior of a function is changing. So first, serverless at Google. So serverless at Google comes in two flavors. We have App Engine and we have Cloud Functions. So with App Engine, you build web applications, and these applications respond to HTTP requests. With functions, you create small code snippets, and they respond to events. So further in this talk, whenever I talk about applications, I mean App Engine applications. And when I talk about functions, I'm talking about cloud functions. So how do we build serverless at Google? So first, you need to, we start with data center, or rather with data centers all around the world. And they're running like physical machines, so indeed there are servers in serverless. On the top of that, we have Borg. So Borg is a large-scale cluster management system at Google. So if you think about any Google-hosted service, it's actually run on Borg. But the thing with Borg is that it's used to run Google code, so trusted code that we develop at Google. So the question is what we can do with this untrusted code and that you developers provide. So we put this code, or rather the running version, so like a binary or something of this kind, to gvisor. And gvisor is recently open sourced a virtualization layer for processes. So it adds like a layer of isolation. So different processes can be run separately in this trusted environment. On the top of that, we have serving, routing, and scheduling. So anything that is needed to actually route your request to the right instance, and also scheduling, so creating and evicting instances, and like this kind of like middleware logic is put there. And at the front, we have Google Frontend, GFE. So Google Frontend is like reverse proxy that allows like any traffic that comes to Google to be routed to a specific service, including Cloud Functions, including App Engine. So this was like a high-level design architecture of serverless. Now let's look at what happens when you deploy a function and what happens when the request is coming and needs to be routed to your function. So first, deployment. Let's assume that you are using gcloud. So gcloud is command line tool that we use to manage all resources in Google Cloud. And if you type command app deploy, you will be deploying an App Engine application. If you type functions deploy, you will be deploying a function. And let's assume for a while that you have a code in your current directory. You're executing this gcloud deploy command. So first, what we are going to do is we are going to upload this code to the cloud, because actual build happens in a cloud. So if you are using, in example, Node.js, and your file, like source code, is associated with Node with package.json file, we'll take dependencies to the finder. We'll call npm repository, fetch the dependencies, and build your function. And then we are creating a function on our infrastructure. And there are two things that mainly contribute the additional latency that you may see. These are cold starts and running deploy. So I will be talking about that in a second. Also, what is worth mentioning, we cache dependencies that you are using. That's why on the first deployment, you will likely to see like a longer latency. However, any consecutive deployment should be much faster, because it's likely that you modified some code, but not all of them. So maybe the dependencies are already resolved and we don't have to rebuild them. And rolling deploy, so deployment is eventually consistent. So when deployment is successful, it doesn't mean that all functions that are actually running are running the new version. Because it may happen that during deployment, requests were being processed. So we are not going to like stop processing these requests, but we allow some time so they can finish. And we're rolling out this update. So maybe you need like a few seconds, or maybe dozen or so seconds for the new version to be fully running in production. And now serving. So what happens when request, like a user request, is coming to our servers? So if there are not enough instances of functions, we need to create a new instance. And this is when where a cold start appears. So we need to load your function to the memory and execute everything what is in the global scope. So it introduces the additional latency that you will observe when running Cloud Functions. So here I would like to do a quick retour, which is like relevant, but it's not exactly on the main track. So concurrency and billing. So these two models, functions and applications, are quite different. So in functions, you are billed per request. So you are billed exactly for the time the requests were executing. And it's independent from the function instances. So you shouldn't be concerned about how many instances need to be created in order to handle your traffic. You're interested only about the request time. It's very different for applications, because for applications you are paying for instances that are serving traffic. And because applications are usually multi-threaded, the cost of the running instance doesn't depend on the number of requests. So let's say that a single instance can handle from 1 to 20 requests. Then no matter how many requests there are, you will be paying just for the instance. And the important thing is that the first model implies that functions are single concurrent. So there's always one-to-one mapping between a request and an instance. Let's look at the cold start, because this is like very relevant. So you can think about how cold start duration and cold start frequency may impact your service. So it's very likely that you will be in one of these two places. If you're running an application, it's very likely that it needs to do some preloading at the startup, maybe it needs to fetch some data. So the cold start takes time. However, it's very infrequent due to the reason that I mentioned previously. So the fact that application can process many requests, so the number of instances scales slower. Whereas for functions, like functions can be created and evicted at any point of time. Like any traffic change actually triggers changes in the number of function instances. So you should aim for like very short cold starts. There's another point where you don't want to be. So you don't want to have both like very long cold starts and very frequent cold starts. And finally, there's this like sweet spot where you would like to be, but it's not very likely that you will be privileged to be in the place when you have like very lightweight service and very infrequent cold starts. So it's create like a boundary, create a definition of an application and a function in serverless. So applications are usually multi-purpose. They have some shared state, and they are multi-threaded. Whereas functions are like very small single-purpose units, and they are single concurrent. So let's go back to the main track. Compute time and threads. So let's think how CPU time of an instance, application instance, function instance, behave over time. So let's assume that there are two requests, and there's one request that begins and then finishes. There's like a small gap, and there's another request coming. And with applications, like CPU time may look like that. So there's some spike the request is using, there is some post-processing that is outside the request scope, and there's another request, so we see the spike again. But in functions, it will look very different because of this billing model and single concurrency. The fact that you are built just for the request time implies that you cannot use processor outside the request scope. You need to assume that CPU will be throttled to 0 once you finish processing the request. So that's why for applications, you can really think what processing you can do outside the request scope, because you are just using an instance, so you can do whatever you want. However, with functions, you are just bound to the time when the request is being processed. So this is also the thing that you should think of when writing a serverless service. So if there's just like tiny amount of post-processing, maybe it's just fine to use it in the function. So do some callback before returning the response to the user. Otherwise, maybe you should use App Engine. The other thing that you can do, you can instrument your functions. So you can delegate this post-processing to another function, and you can use Cloud PubSub for that. So Cloud PubSub is a messaging system that we have at Google Cloud. And now instance eviction. So when traffic increases and new instances are added in the system. But also if traffic goes down and the instances are not needed, they're evicted. However, the thing that you should know is that this eviction is lazy. So it's not that, immediately after the request was processed, the instance will be deleted. The lifetime is indeterminate. It may be a matter of minutes, but it may be in a matter of hours. However, like eventually, it probably will be evicted. But it's you can assume that the platform is smart, so we'll not try to delete an instance if it expects any traffic, and also if it's not scarce for resources, then you can probably leave it in the memory because it doesn't matter. And patterns and anti-patterns. So here I named a few. The first one is just using the long primitive. So using a function when you probably should choose an application and on the contrary. The second is avoiding call starts because there's a cost associated with call starts. Also the background processing, so processing or something outside the request scope. Also because you don't have control on the number of instances, you may have a problem. In example, if your function connects to a database, because there is like a connection pool which may be easily exceeded because you don't have a control of the number of function instances, and also idempotency. So for applications, you have these asynchronous HTTP requests. However, for functions, you have events, and they are running in like at least one semantic. So you also probably need to think about how your function will behave if it was executed more than one time. So let's look at the top of these anti-patterns. So let's say that I have a very big Java monolithic application that I would like to move to cloud. And the question is whether can I put it to cloud functions? Probably not because of the cold starts and resources available. The question is, can I move it to App Engine? Maybe it's appropriate, but it really depends on your applications. Probably the best thing you can do is to divide this monolithic application to some smaller services, so you can leverage the benefits of using either App Engine or Cloud Functions. The cold start. So you shouldn't depend that much on in-memory state. It's still fine for using example on the best effort basis. However, if you need high guarantees on the example like in-memory cache, you should probably use a database or remote cache. The timestamp, so you should really think what's executed in the global scope, what is executed just once, and what is executed just as a part of actual request processing. Java is pretty expensive, so you should look for ways to decrease the initial startup time. And finally, simply choosing the wrong primitive. So really think what's an application and what's a function. So here is example. So it's very common to put many functions in a single file, just for simplicity. And let's say that I have a file like that, and I deployed do something function as a one function and do something else function as another function. And like it looks okay until we realize that one function is using one library that is loaded in the global scope, and the other is using the other library. So we still have to, for each function, load a library that is not used in the code. So it introduced like additional latency on the cold start that decreases the latency that this function in the running environment. So we could do also something like that. So you have something like two functions that are merged. So based on the query parameter, you are doing something different. However, still you need to load these two libraries in the global scope. However, you can imagine that the first condition is evaluated to true maybe one time in 1,000, but you still need to pay for loading all these libraries in every invocation when a new instance needs to be created. So maybe you could do something like this, which still is far from being optimal and looks really, really bad. However, at least it solves a problem of very long cold starts. But like I said, it's still the wrong thing to do. So now I would like to introduce Marcin, who will talk about real-life example, not these very obscure sample codes.
Okay, thank you. Okay, so I will present you now a short function, and I will do a few that is maybe not written in a very idiomatic way, and then I will walk through a few optimizations that I've applied to this function. And this will be a semi-live demo. I mean, I already ran some load tests on this function to save some time during the presentation, as I wanted to have more than one QPS on this. Okay, so the function would be rather simple. It will be a function that will take an image and text and create a new image. So how it will work? It will fetch the background image from cloud storage. Cloud storage is Google NoSQL database that you can use in Google Cloud Platform. So after fetching this background, the function will apply caption that will be provided in the request by the user. The function then will use the ImageMagick library to merge the background in the caption, and then the result will be uploaded to Google Cloud Storage again to some different path. And we also add an option to not use the background, so it will be just like print an image. Okay. So the function code would look like this. So if there's no, the rec is the request, HTTP request object, and we will extract the parameters I've mentioned a moment ago from the object. If there's no caption, we will use hello world caption. Then if the background, we will decide whether to use the background or not. Then we create a temporary directory where we store the result after ImageMagick processes it, and then we upload it to the bucket. Okay, so and for these tests, I already ran Artillery, which is like a tool for load testing written in Node. And I did 5 QPS for 5 minutes. So let me go to the results of the test, as I have them here in the Cloud Console. So here I have first version of the function, which is roughly the code I presented you on the slide before. And here, this is the Cloud Console, which is UI for Google Cloud. And let's take a look at the invocations that. So one invocation here is one execution of the functions. So here we can see we had approximately 5 QPS, which is what I just mentioned. But we can also see that some of the invocations didn't succeed, right? Like if we turn this off, there's something wrong going on here. And we can see that the problems were out-of-memory errors, which is a bit weird because, as we can see, this function have 256 megabytes of RAM, and we are doing very simple processing here. So if you look here, we can see that 95 percentile was almost at the cap. So how about we try to increase the memory limit for this function, which is a thing we can do in Cloud Functions. I'm not sure if this is visible from the end, or should I zoom? Yeah, okay, sorry. I should have asked at the start. Hey, so this is the result of the load test I've done, and here we have a graph of memory usage over time, and we have some information about this function. For example, which region it is, and how much memory it has allocated. So one of the things you can do, maybe to solve this problem, is to allocate more memory. So I already have a function prepared with more memory, 500 megs. And let's see how it worked. So this test was run in the morning. Let's see invocation across last 6 hours. And we can still see there were some out-of-memory errors. Maybe not as many as before, because only 1/10 of the QPS, but still some. Oh, this is not errors. It's really inconvenient to use touchpad and look at the projection. Okay, so we can see that error ratio has fallen down, but it's still non-zero, even though we have half gig of memory. So what's up with that? Are Cloud Functions so not optimal? Well, if we look at the source code here, we can see that we start with creating a temp local directory, and then this temp local directory is being used to write some files to, right? We have this background file, and then we upload this file to cloud storage, but we never delete it from temp directory. So that's a memory leak. So what happens here is that Cloud Functions across different subsequent invocation reuse the same instance, which shares the same temporary disk space, and this disk space probably fills up. Okay, so how about we optimize this and we actually delete the temp file. So I have this function prepared. If we go to the source. So this source, by the way, this source contains a few files because I have some boilerplate and a package.json file which contains the dependencies. But the meat of the function is here. So how about we actually delete this temporary result? Let's see how this worked. Great, no out-of-memory errors. And let's take a look at memory usage now. So it's well below 500 megabytes. So does it mean we could now decrease this limit again to 256? Well, not really, because how Cloud Functions work is that there's only one knob for resources allocated, which is both memory and CPU time. So decreasing the memory here would also mean less CPU time, so it could mean bigger latency for the functions. Okay, so speaking of latency, we also have a metric for it by default, and as you can see, we can view the percentiles of latency, and it seems to be quite slow. Like, we are doing very simple manipulation, and 50 percentile is what? Almost 2 seconds? Okay, so let's try to debug this. So in Cloud Console, we can access logs for each function invocation. Let's load some logs. And here, you can see the function name, the timestamp when the invocation took place, the unique invocation ID, and the log message we produced. So this is a bit non-readable. So let's limit ourselves only to one execution ID, like this. So here, uploading of this file takes almost over 1 second, which is quite slow. Maybe that's because this is an uncompressed BMP file, and we could use some better format. So what I'm trying to get here, the point is that the infrastructure is not a silver bullet. It's not magic. So if you have some non-optimal logic inside the function, well, the best infrastructure won't help you. And in this case, the logic is non-optimal because we are using this data format that is not very good. So if we compress this, we can probably get better results when uploading to cloud storage. So let's see the next incarnation of this function. Is this really faster or not? Let's check execution time. And 50 percentile is also around second, but seems to be slow. Seems to be better than the previous one. Okay, now I have to scroll back here. Right, so here we have 50 percentile of 1.7, and here we have 1 second. Nice. Hey, so what else can we improve here? So Monika mentioned cold starts. So if we go to the source, you can see this background file is downloaded on each execution from the cloud storage. So maybe instead we could reuse this across invocation in the same instance. And I have code for this over here. Right, we have this background downloaded variable, and if it's true, we set it true and we download it, and then we don't re-download the file. So let's see if this is better. No, not invocations. And we got our 50 percentile under the second, which is better. So what else is happening here? We have also this cloud storage here, which is abbreviated GCS, like Google Cloud Storage, and we recreate the connection to cloud storage on every invocation. So how about we create this only once, like this? So here, outside the function, we no, here, not here. Yeah, over here we create the GCS connection. Let's take a look. The 50 percentile didn't go down by that much. The 99th percentile got down quite a bit. And I think those are all optimizations that I wanted to show you. So to recap all of this, first, let's not leak memory when writing functions. Second, think about the instance size. Bigger instances can be better. Third, remember that it's still important to optimize the application code, even despite how good the infrastructure is. Fourth, lazy download the resources that you use, and don't re-download them on every invocation. And fifth, use global scope, well, when it's possible.